Alright, welcome back to the PyCSE channel. Today I'm going to talk about the little book that I wrote recently on regression in scipy. And regression is basically you have some data, you have an equation with some parameters, and you want to find the best set of parameters to fit your data. And there's lots of different kinds of regression, and Numpy and scipy and other libraries in Python support a lot of different options, so I wrote about them in this book. So we talk about linear, nonlinear, robust regression, polynomials, some goodness of fit. We have some uncertainty quantification, and I'll go through a couple of things. So the first thing we do is talk about how to get the data. We use a lot of the data files that are provided by NIST for testing regression algorithms. And they're interesting data files that are challenging to fit in some ways. But most importantly, NIST has declared what the right values are, and you can use those values to test any algorithm you're coming up with to see if it's the right idea. So we use URLlib to download these files directly from NIST so that we get files that have all the data in them. All right, over here in linear regression, I start out with polynomial fitting because it's one of the simplest ways to fit data. You just load data, and you can use polyfit, specify an order, and that's it. If you use a second order, put a 2 here, you get a quadratic equation. And it's very straightforward to fit a polynomial. We talk a little bit about the so-called normal equation, which is an analytical solution for linear regression. And when you have an equation like xb equals y, then you can work out that you get x transpose x inverse, x transpose x, and you can use that to find the solution to your equation. And it's kind of nice. It's not how people generally do least squares, but it's interesting to be able to work it out. Then I go through a couple of functions in Numpy and scipy. We have the least squares. We have least squares linear. That allows you to put bounds on the parameters. There's NNLS, which makes sure that every parameter is 0 or positive, so a constrained regression. There's a linregress in the stats function in scipy. It's very specialized and does some statistical tests to tell you whether your slope is significant. And then we finish this up with some functions in PyCSE that I created for uncertainty quantification. And so PyCSE.regress will give you the confidence intervals and standard errors on all of the parameters that you want. And so you can see here, like here are some confidence intervals on the parameters, and some of these include 0, which is an indication that that these parameters are not that significant because there's a reasonable probability they could be actually 0. And then I show some work from our group recently on using delta method for prediction errors. So we can get confidence intervals on parameters from PyCSE.regress, and you can use a different approach to get the prediction interval on your data. And so that ends up looking like this. This is where we would predict values to come. Then we talk about nonlinear regression. This is any model where the parameters are in the model in a nonlinear way. And for example, x to the p, or here we have some nonlinear combinations of p or e to the px, or any of those are nonlinear. And for those we need something like least squares. And this is an iterative approach that uses optimization to find the answers. And there's a whole bunch of them. We work our way through least squares. This is an older version of that, least SQ. And those are both now wrapped into something called curve fit, which is a little more convenient. You define a model function, and curve fit gives you the optimal parameters and an estimate of the parameter covariance. And we use that in PyCSE, so I wrap that around there so that we can also get confidence intervals from that covariance matrix. And similar to the delta method in linear regression, we can also do the delta method in nonlinear regression. And this is also now feature in PyCSE, and you can read about it in here, how we get the derivatives and how we do all of the analysis, but it ends up giving us the same thing. All right, those are the two main ways people do regression. There's a concept called orthogonal distance regression that's kind of shown here. So in the previous examples, you would minimize the vertical distance in the fits, but sometimes when you have uncertainty in the x values, it makes sense to also minimize in the x direction. And a way to do that is this so-called orthogonal distance regression, where you minimize the distance of a point to the tangent of a curve. And there is a package within scipy that does this orthogonal distance regression, and I show a couple of examples just to show how it works. Next, we talk about robust regression methods. So all of the examples before this were minimizing some squared errors, and if you have outliers, then because you square the error, outliers have a big effect on the fit, and so we call that a non-robust fit. And there's a bunch of other ways you can minimize the effect of outliers on regression by either minimizing the median squared error or the mean absolute error, or something called the LP norm, where P is between 1 and 2. So these are, the mean absolute error is like a L1 norm, and both of these, or all three of these, are ways to do it. And so I show some examples of how to do robust regression in here, using curve fit and using minimize. And they're all great ways to reduce the impact of outliers. I spend a little bit of time talking about goodness of fit assessments. So it's easy to do the fits. We're on page 63, and we've done lots of fits now. And it's important to be able to evaluate, is this, for example, a good fit, or is it overfitted? And there's many ways to do it. You can look at the residuals. So we talk about that. These look like they're kind of randomly scattered. And you can see here it's at least approximately Gaussian distributed. And those are good indications that your model is not overfitting. We can do some metrics on the average of the residuals, mean squared errors, etc. We show some methods to determine if your residuals are normally distributed using analysis, and then we put it all together to figure out how do you know if your model is reasonable and something you should use. All right, and there's a few miscellaneous topics on outlier detection, some statistical approaches to doing it, and using weighted regression techniques to minimize the effects of outliers by putting a lower weight on them, and some kind of case studies and using optimization directly. And then finally we finish out with some more advanced modules that are used in regression. So if you don't want to build everything out yourself like it's been done so far, you can go towards statsmodels for linear models. And statsmodels is nice. It gives you a lot of very detailed statistical analysis, degree of freedom analysis. This is Bayesian information criterion, and this is something similar. There's constants, errors, t-values, etc. lmfit is a package for nonlinear least squares minimization, and there's examples of that. This also gives you these different kinds of analysis, even correlations and so forth. We talk a little bit about sklearn. It is a plotting package that makes it easy to do statistical analysis, and very briefly touch on sklearn or scikit-learn as the next step in data-driven modeling. All right, so that is it in the new book on regression in scipy. You can find the link to it in the video description. And if you need to do more advanced types of regression, you may find a lot of helpful information in this booklet. The next booklet out will focus on data-driven modeling, which is kind of going deeper into the sklearn framework and thinking about how do we build models from data when we don't know the functional form that we want to use, which is what this book focused on. All right, that's it. I hope you get a chance to look at it, and if you do, leave a rating on the booklet so that other people know if it's helpful. Thanks.